Welcome to my YouTube channel. So today I will discuss the differentiability and CR equations in complex analysis. So let's start. So definition of differentiability of a function. A complex function f from D to C, that is, this function is defined on this set D, which is non-empty and subset of the set of complex numbers. This function is said to be differentiable at z0. Z0 belongs to this set if this limit z tends to z0, fz minus f of z0 divided by z minus z0 exists, and this limit can also be written as limit h tends to 0 f of z0 plus h minus f of z0 divided by h. So whenever this limit exists, we say this function is differentiable. So from this we get this is general form, and if we put z minus z0 equal to h, then we get this form. So you can remember this form, and the value of the derivative of f at z0 is denoted by this f dash z0, and it is written as this f of z0 plus h minus f of z0 divided by h. So this is the value of the derivative of this function f at z0, which is belongs to D. So this is the definition of derivatives of a function, that is differentiability. So a function is differentiable whenever this derivative exists, and this function f is said to be differentiable in this set D if it is differentiable at every point of D. So this is D, which contains z0, and this contained in complex set of complex numbers. So this is D, this is z0. Whenever at each point of D this f function is differentiable, then we say this function is differentiable in D or on D. And whenever this function is differentiable at every point of this complex plane, that is entire complex plane, whenever this function is differentiable in the entire complex plane, then we say this function is entire function. Okay. So this lecture will be very beneficial for the students of IIIT Bhagalpur. So from this chapter, there will be many questions in your exam. So learn. So let us take a theorem. So this is very important. A real valued function of a complex variable, that is, function is defined on the complex set, but its value will be real. So from C to R, this is called real valued function of complex variable. That is, whenever we take z from C, this will give a real number. Okay. So this type of function either has derivative 0 or the derivative does not exist. So the derivative at any point A in this plane will be limit h tends to 0 f of a plus h minus f of a divided by h. So h is this, that is h1 plus I h2. So here this is h1 and this is h2. This is real axis, this is imaginary axis. Okay. So h can be approaches to 0 along x-axis or along y-axis. So first, if we take h equal to h1 plus I into 0, that is h2 equal to 0. So this become this point, this is A. So then now we take h1 tends to 0, that is if we take h tends to 0 along real axis. Okay. So along real axis, so this limit, this f dash a will be real. Okay. Or if we take this h equal to 0 plus I into h2, that is real part 0, imaginary part is here. So h2. So now if h2 tends to 0, that is h2 is this. So from this, so along imaginary axis, so if we take h tends to 0 along imaginary axis, then this value f dash a will be purely imaginary. So therefore from this we can conclude that f dash 0 must be 0. So this is the proof. This is the proof of this theorem. So this is very important. This just two steps. So first you write this definition of derivative at a point A and take h tends to 0 along a real axis, and this will give f dash a real value. And if we take h tends to 0 along imaginary axis, then the f dash a will be purely imaginary number. So from this we can conclude that f dash a must be 0. Okay, or does not exist. So this real and this is purely imaginary. So these are two different. So limit only exists when these are path independent. So this is path dependent. Whenever along real axis we get real number. Whenever along purely, whenever we h tends to 0 along imaginary, so we get two different values. So one purely imaginary and one real. So it is path independent. That means the derivative does not exist, or if exists it must be 0. That is the reason. So this is very important. So this is another theorem which is very important. So see what happens if the function f has derivative at z0, that is f is differentiable function at z0, then it is continuous at z0. So whenever differentiable, this implies continuity. Okay, differentiability implies continuity. So this happened, but if we prove that this f is not differentiable, this does not imply that f is not continuous. So many students uses this theorem in a wrong way. So some students, if they are asking that so that f is continuous or discontinuous, so they first see that f is differentiable or not. If f is not differentiable, they conclude that f is not continuous, but this is not right. So this is the theorem. Differentiability of a function implies continuity of that function, but not differentiable does not imply not continuity. But for this, contrapositively, we can say that f is not continuous implies that f is not differentiable. So see what is the difference. Differentiable implies continuity, but if we add not both sides, it will not happen. Sometimes you assume that a less than b, but whenever you add negative term, that is a minus a less than minus b, this will not happen. This sign will change. So you can think similarly, and this is a logic. That is, if a implies b, from that we can say not b implies not a. But from this we cannot say that not a implies not b. So this is color. This is not true. So you can remember by this. So a less than b, whenever we multiply negative, so minus a less than minus b, this is not true whenever this is true. But opposite is true. Minus a greater than minus b. Whenever this is true, this is true. Similarly, whenever this is true, then contrapositively we can say not continuous means not differentiable. But not differentiable does not imply that not continuous by continuity of that function. So this is very important. You can use many times. You can use in some problems whenever solving or you are trying to solve show that f is continuous or discontinuous. You can use this, but see how can you use. So this is the meaning of that theorem. So let us define what is definition of analytic function. So a function f is said to be analytic. Sometimes it's called holomorphic function. At a point a in set of complex numbers if it is differentiable. This is very important. If it is differentiable at every point of some neighborhood of A. So A belongs to this C. So this function f is said to be analytic at this point A if it is differentiable at every point of some neighborhood of A. So if this is neighborhood of A, that is, you can say this neighborhood. This is neighborhood of A, neighborhood of A, neighborhood of A. This is neighborhood of A. So whenever at each point of this neighborhood of A, f is differentiable, then we say this function is analytic or sometimes called holomorphic. But it is not mentioned that the function need to be differentiable at this point A. Okay. So neighborhood means it contains in this neighborhood. So wherever this function is differentiable at each point of some neighborhood of A, then the function is called analytic function at this point A. Okay. So now we discuss this theorem which is related to Cauchy-Riemann equation, which is called CR equations. So this is theorem 3.17. Remember the number of this theorem 3.17. We will use later. So if fz equal to uxy plus ivxy, that is real function and this is complex function, is differentiable. So whenever f differentiable at this point z0 equal to x0 plus iy0, then CR equation hold at this. So CR equation satisfied. Whenever differentiable, f differentiable, so CR equation hold at z0. So CR equation is this. So in general this, so from this we can get ux equal to vy and uy equal to minus vx. We will get this from this. So now we prove this theorem. So for that, first we let, this is proof of this theorem, this is very important. So let f is a function from D to C, where D is the subset of C, and if f is differentiable at z0 equal to x0 plus iy0, then the limit, that is limit h tends to 0, f of z0 plus h minus f of z0 divided by h exist and exist. That means this limit, that is called f dash z0, value of the limit, this f dash z0 will be path independent. So this is very important. We use this to prove this theorem. So simply f is differentiable, this is given. So whenever f is differentiable, this limit exists. So value of the limit is f dash z0 whenever this limit exists. So limit exists when the limit exists, whenever this limit is path independent. Whenever we choose h tends to 0 along any path, so the value of this limit will be same. So this limit f dash z0 will be path independent. So now we use this concept to find this value f dash z0, and we find for two different paths, and we equal the left hand side, that is f dash z0, and then we will get this. Let's see. So this is the value of f of z0, limit h tends to z0, and this is the same. So now just we take in another form. So we take h equal to h1 plus I h2, and z0 is given x0 plus I y0. So z0 plus h will be x0 plus h1 plus I into y0 plus h2, and h is this vector, that is complex number. So this will be h2 and this will be h1. So this is real axis, this is imaginary axis. So just by putting this value we get, and we can write this in the form, that is x0 plus h1, y0 plus h2, that is f of this, and minus f of x0 y0, and we just put this, and then h tends to 0 will be this h1 tends to 0 and h2 tends to 0. So h tends to 0 means h1 tends to 0, h2 tends to 0. So we write in this form. So now we take h equal to h1 plus I into 0. That is, we take h2 equal to 0, h2 equal to 0. So this will be the h1 value, that is h equal to h1. Now this formula becomes, so this is means we take h tends to 0 along real axis in the proof of previous example, like that. So when h tends to 0 means whenever we take h tends to 0 as along real axis, so from this we get f dash z0 equal to limit, so h2 already 0, so we can write h1 tends to 0 and this will be h1, so x0 plus h1 and h2 is 0, so that is y0 minus f of x0 y0, see, and this will be h1 and plus I into 0. Okay, so this is, so if we write in this manner, so from this you get, this is nothing but, so see, this is del f del x at z0, that is x0 y0, that is del f del x x0 y0, the definition of this is, so we can write this, so we rename it by 1, and whenever we take h equal to 0 plus I into h2, that is whenever we take h1 equal to 0, so this will be h2 and h tends to 0 implies that h2 tends to 0. So from this we get f dash z0 equal to limit h2 tends to 0 and this will be f of x0 plus h1 is 0 comma y0 plus h2 minus f of x0 comma y0 divided by h10 plus I into h2. Okay, so if we common 1 by I, so if we write like this I here, so if you write I 1 by I here, so limit h tends to 0 f of x0 comma y0 plus h2 minus this by divided by h2 is nothing but del f del y at x0 y0, that is z0. So this is 2. So simply, as this is path independent, so this limit exists whenever f is differentiable at z0, means this limit exists at z0, and from this limit we get f dash z0 del f del x z0, which is 1, and also whenever we take along another path, so here we take along x-axis and here we take h tends to 0 along imaginary axis, so we get f dash z0 is 1 by I del f del y z0. So as this limit is path independent, so for these two different paths this value will be same. So now we, so as this limit is path independent, as path independent, why path independent? This because this f is differentiable at z0, so the limit exists means the limit is path independent. So for two different paths we get two different value, so this will be equal, that is del f del x at z0 equal to 1 by I del f del y at z0. So you can write from here fx z0 and I is multiplied by here, and this is f y z0. So this is the Cauchy-Riemann equation, and from this you can write, so as f is u xy plus I v xy as a function of xy u v, so f of x equal to ux plus I vx and f of y equal to uy plus I vy. Now if we put here this value, so I into ux plus I vx equal to uy plus I vy, and if you multiply this I ux, this will be minus dx equal to uy plus I vy. But just compare real parts and imaginary parts. So this is real parts, so that is uy equal to minus dx, and imaginary part, that is ux equal to vy. So ux equal to vy. this is also the CR equation. So obviously this will be 0 0 x0 y0. Okay, x0 y0. As f is differentiable at z0 equal to x0 y0, then these two equations are satisfied at x0 y0, that is z0. So this is called Cauchy-Riemann equations. So this is the proof. So this is very important theorem, and proof also very important for the exam, especially for students of Triple Bhagalpur. So this is very important theorem to check whether the given function is differentiable or not. So CR equation also very important, because whenever f is differentiable at a point, so CR equation is satisfied or hold at that point z0. Okay. So whenever differentiable, CR equation hold. And to check differentiability of a function, we check CR equation hold or not. So this implies this. So contrapositively, if this not hold at that point or at that point, we can say f is not differentiable. But not differentiable does not imply that CR equation does not hold. There may be that CR equation hold, but it is not differentiable. So there is many example. I will cover that not differentiable, but CR equation hold. Okay, CR equation satisfied but not differentiable. That means this implies this. So not differentiable does not imply CR equation does not hold. CR equation hold. And to check differentiability of a function, we see the CR equation at that point satisfied or not. If not, then we say it is not differentiable function. So CR equation generally used for non-differentiability. So to check non-differentiability of a given function. Okay. So like that, there is another theorem which is also very important for some special type of functions. So a necessary condition for a complex value function f u plus iv to be differentiable at z0 is this: if z bar not z, z is x plus iy and z bar is complex, that is x minus iy. So whenever derivative with respect to z bar at that point equal to 0, so whenever differentiable f is differentiable at z0, this implies that f z bar z0 will be 0. So this will be also used for used to check non-differentiability of a function. Like if we take these two functions, f of z equal to z bar. So from this we can see f z bar equal to 1. So at any point this is not equal to 0. So this function is not differentiable at any point. Okay. Similarly, gz, that is real z, can be written as z plus z bar divided by 2. That is z by 2 plus z bar by 2. So g, derivative of g with respect to z bar will be 1 by 2. This is never be equal to 0 for any point. So this function also not differentiable. So this theorem is uses for special type of function to check this function is not differentiable. So necessary condition means this condition will be hold whenever the result happen. That is, if whenever f differentiable at that point, this condition will be hold. And sufficient means sufficient condition. So to be differentiable, this condition must be hold. So whenever this condition hold will imply this, we say that this condition is sufficient. Okay. So this is not sufficient condition, and also CR equation at z0 is not sufficient. Is not sufficient condition to be differentiable, but it is necessary condition. That is, if differentiable at z0, then CR equation hold at z0. This is called necessary condition. But this will be sufficient with if we add another condition. So, like let us take let us write one theorem. So we have seen in the previous theorem that differentiability implies that CR equation hold, but converse is not true. That is, if we see that CR equation hold at a point z0, then we cannot conclude that the function is differentiable. So this CR equation is a necessary condition for a function to be differentiable, but this is not sufficient. But this condition will be sufficient if one condition will be added in the theorem. So this is the theorem. So this is the function f from b to c. D is the subset of c. C is the number of complex set of complex numbers, and fz is uxy plus ivxy, and z is x plus iy. So suppose that this partial derivative, so ux, uy, vx and vy exist at each point in a neighborhood of z0 and are continuous. So these four partial derivatives exist at each point of a neighborhood of that point and are continuous. And second condition is CR equations are valid at z0. Then we can conclude that f is differentiable at z0, and it can be written as this with respect to x, and also can be written as with respect to y also. No, you can write ux equal to uy and uy equal to minus a. So you can put here as CR equations are satisfied. So this is the theorem, very important theorem. So CR equation valid does not imply differentiability, but whenever we add this another condition, that is four partial derivatives exist and are continuous, then we say this is differentiable. So this is another thing I will discuss. This is the last definition of this lecture. So harmonic function, a real valued function phi of xy, that is function of xy, said to be harmonic function in an open subset D of C if it has continuous partial derivative of second order, and satisfies the Laplace equation in two variables. That is this is Laplace equation. So whenever phi satisfies Laplace equation and has continuous partial derivatives, then we say that phi is harmonic function. So throughout this Laplace equation satisfied. So where this nabla 2 phi is this. So f equal to u plus iv. We will talk about the u and v is harmonic function whenever del 2u del x2 plus del 2u del y2 equal to 0, or this, if this v satisfied this, then v is harmonic function. Okay. So this is called harmonic function, the real valued function. So for today that's it. So if you like it, please subscribe and like it and share with your friends, and this lecture will be very beneficial, especially for the student of AAA Bhagalpur, and I will cover all the examples and previous year questions related to differentiability and shear equations in the next lecture or next video. So before that video, watch this carefully and understand what is happening in this lecture and what is the concept of differentiability and shear equations and the theorems I have discussed. So that will be very beneficial to understand the solution of each problem which I will discuss in the next video. So thank you. Share with your friends. Thank you very much.